Hello all, welcome to my course on methods of adhesion measurement, theory and practice. We are at lecture 46 today and we are discussing about a sandwich layer of adhesive between two parallel discs. We had started the discussion in the last lecture in which we have this compressible elastic film that is bonded to the bottom disc over here, and in the top surface it is in slipless contact. And so we apply some amount of load either in compression or in tension, and we want to know that what kind of pressure profile that develops in this elastic film. And we carried out these calculations and this analysis for an incompressible elastic film in the last lecture, where we developed that this is the critical pull up stress is given by this kind of equation. In the case of this contact, the slipless contact at the top surface, the film top surface interface. And we also extended this calculation for an compressible sandwich film, and for that case we derived this expression, this equation, and the solution of this equation was given by this modified Bessel function of the first kind, where a is the radius of this disc and then I0 represents this modified Bessel function of the first kind, and capital K here is the bulk modulus, h is the thickness, and so on, and mu is the modulus, shear modulus. So today we will like to find out what is the force total pressure, okay, that is applied. So pressure distribution is given by this equation, and this is the total pressure. So the total pressure can be obtained by integrating over the area. So that is 2 pi r into p r into d r from 0 to a, and 2 pi p r is given by this expression. So this is k delta by h into 0 to a into 2 pi r into 1 minus I 0 r of L, and L is a characteristic length scale over here that is comes from the material properties, and then k delta by h. So delta is the vertical deformation at the surface, at the top surface at j is equal to h. So here we can have write it as k delta by h into 2 pi r, 2 pi, and let us say it is r into dr. So let us say this is r square by 2 and 0 to a here, and then minus this is 0 to a, and this is r into I0 of r by L by I0 a by L and dr. So this part, this we can write further as, let us say, k delta by h into 2 pi into a square by 2, and minus, let us write it as L square, and let us write it as a over L, and it is 0, and here it is r by L and I0 r by L, this is I0 a by L and d of r by L. So this is the way I have. So in a sense I have multiplied by L square here, and I have derived, I have divided this L over here r by L and here d of r by L. So in a sense what I have here is something like this: x of I0 of x, d of x, and 0 to let us say this is a over L, which is fine like this. So and here I have 1 upon I0 of a by L like that. So it so happens, so now we need to find out that what will be this integration. So this integration is given by x of I0 I1 actually. So R0 is the 0, it is the order of this Bessel function, and this x in the parenthesis, this is known as the modulus of this function, of this Bessel function. So there are tables available and you can have a look at it, and integration tables, and that will give that this x I0 of x dx, that after integration this comes out to be x into I1 of x, and so here it is written here. So the whatever I wrote there is over here basically, and so here I have k delta by h, and this is pi a square. So pi a square comes from here. So this is pi a square by here, and here actually I have divided by a square here and multiplied by a square here, and that let me write it over here and then go to the next slide. So k delta by h into this is 2 pi. So let us say it is pi a square, and minus this is 2 pi into a square into 1 upon a by L, okay, whole square, and this is I0 by a by L, and this is into this is 0 to a by L, and this is r by L, and I0 of r by L, and this is d of r by L. So that is what we are integrating over here, and this portion, this will give rise to r by L into I1 of r by L, and this is 0 to a by L, like this. So this is the first order of order 1, this modified Bessel function of the first kind. So this is I is modified Bessel function of the first kind, and 1 means this is the of order 1. So that is what has been written here, and this modified this Bessel functions and also the modified Bessel functions, these are expressed in this kind of series series where x is the modulus. So it is given like that, I1 of x is given by this equation. So x into I1x will be like this. So if we let us say want to divide let us say x into I1x, so let us say x into I1x by I0x, okay. So this will be equal to, so this is x I0 is 1 plus this is x square by 4 plus let us say x to the power 4 by 4 into 16 over here, and xi, so it is x square by 2 into 1 plus this is x square by 8 plus this is x to the power 4 by this is 32 into this is xi, right, 32 into 6, this is 32 into 6, 32 into 6, right, and so on, and here also so on. So we can now divide this the numerator by this denominator. So let us try to do that. 1 plus x square by 4 plus this is x to the power 4 by 64, let us say, this is like this, x square by 2 plus let us say this is x to the power 4 by 16 plus I am just multiplying by x square by 2 in this inside the bracket. So it is x to the power 6 here, and this is 2 into 32 into 6, so it is 12, like this. Now let us multiply it by x square by 2 here, so it is x square by 2, so it is x square by 2 plus x square by x to the power 4 by 8 plus x to the power 6 by 64 into 2, so whatever it is 128, like this. Subtract it, minus 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 goes, so it will be minus of x square by 16, x to the power 4 by 16, and then it is 32 into 12 into 32 into 4 is 128, so it is 4 here, 128, it is 12 here, 3 here, so it will be, okay, I have already done this actually here. So it comes out to be, okay, I have not done it in the rough work I have done, but here it comes out to be x square by 2 and then minus x 4 to the power 8, and that you can easily do, that I have already done this, so you can further do it, it will come out quite nicely, and this comes out to be here like this, x square by 2 minus x to the power 4 by 16, and so you can write it like this. So this comes out. So by the same way that I was doing here, in fact let me just do it another term. So it is, let us say it is x to the power 4 by 16 here, so it will be minus of x to the power 4 by 16 and then minus the blah blah. So it will be like this, and see we are getting x square by 2 minus x to the power 4 by 16 and all that. So we are getting into these quantities, and that's it. So here finally we will have therefore is equal to this P is equal to k delta h delta by h into, let's say, the pi a square. I will just take it out, then I have 1 minus 2, and then I have let us say 1 by a l square. So yeah, let me see a l, I write it like this, a l square, and this quantity is over here. So this is actually a by l, this is square by 2 into 1 minus this is again a by l, and this is x square by 8 plus this is a by l to the power 4 by 48 and so on. So here therefore we can actually cancel this. So here I have k delta by h into pi a square into 1 minus 1 plus this is a by l whole square by 8 minus a by l whole to the power 4 by 48, okay, blah blah, and this is equal to this gets cancelled. This is 1 here, by the way, this was 1 here, so it's cancelled. So I have here now k delta by h into pi a square into so I can take this a by l whole square by 8 common, so it will be 1 minus this will be a by l square by 6 etc. like this. So it will get simplified like this with this particular term a by l whole square by 6 like that. So this is what I have obtained here. So now one can write total pressure like this, therefore is equal to total pressure, therefore one will write it as k delta by h into here the one that is written k into delta by h into pi into a square into a by l, okay, square by 8 into 1 minus like this. So a by l whole square, what does it give? So that we can actually substitute, and in a sense this is what I have. So let us substitute this 1 by l square over here. So if we substitute that, then it will be, let us say, k delta by h into pi into a square into 1 by 8, and this is a by l square. So it is a square, and 1 by l square is 12 mu by h square into k, sorry about that, h square into k, right, and then this is 1 minus this is a by l square by h and plus like that. Now it so happens that this quantity, okay, will be very small, and since it is very small we can actually neglect this, let us say, and if we can neglect it, then this quantity comes out to be k into delta by h into pi into a square into 1 by 8, and here it is a square into 12 into mu by h square into k, like this. So here you see this k and k can get cancelled, and then of course we are left with 4 into 2 here and into 3 here. So we are left with delta by h into pi into a square into, here it is 3 by 2, so it is 3 by 2, and this is h square over here into mu here, and it is h square over. So the critical the pressure P by pi a square, the average pressure, let us say, so that will be given by delta by h into 3 by 2 into mu by h square, like that. There is a square also here, I have missed it, so it's a square also here, like this. So so therefore this quantity can also be written like this. Now I want to know that how exactly this having this incompressibility or compressibility changes the pressure profile in the film. So, in essence what we have is a film with a modulus mu, shear modulus remains constant for all these films, shear modulus let us say that remains constant, okay, for all these films, and let us say that the Poisson ratio that varies. So, the Poisson ratio here it is 0.3, 0.3 here, 0.4 here, 0.48 here, and let us say it almost goes to incompressibility 0.499, and you are applying some load, total pressure P, and then delta is the deformation at the top surface. So, what it means is that you have this film here which is a disc of course, and between these parallel plates the film remains bonded to this bottom plate, and pressure let us say is applied over here. So, as we said that the pressure will be 0 at the at r is equal to A over here. So, at this is A. So, at r is equal to A the pressure is 0, so which is here, and now we are applying the load. So, the pressure is maximum at the center. Now, how does it go for this different material? So, having different Poisson ratio. So, here in all these cases the pressure distribution is guided by this relation, which is this modified Bessel function of 0th order, modified Bessel function of first kind 0th order, and with like this, and you see that from 0.3 to 0.499 that is a huge increase in the pressure that needs to be applied. So, as we go from compressible to incompressible material, the amount of load that needs to be applied to cause the same amount of delta by H is increases enormously. That is what, okay, this particular plot that I presented here, it shows. So, here it is 0.3, 0.4 and 0.48, and as it goes to closer to the incompressibility where sigma is equal to 0.5, okay, the amount of load that is needed to be applied that increases quite significantly, and that is why this particular data that shows. Now, this was about compression, but in this case also we can apply with a similar approach that we have done it earlier for obtaining the pull of load required to detach this top plate from this adhesive, okay. And here we have just estimated the total load capital P, okay, that is capital, we are writing pull of load. So, I am writing here F here let us say is equal to 3 pi mu delta A to the power 4 by 2 h cube. So, we just derived it, okay, we just obtained it, and so elastic energy will be equal to let us say this is F into delta into d delta, and this is 0 to delta. So, this will be equal to F delta square by 2, and so this will be equal to let us say it is 3 by 4 and pi and mu, and this is delta cube here because delta cube A to the power 4 by h cube, and mechanical energy, okay, potential energy that is minus F into delta, and then surface energy is minus, this is work of adhesion into pi into a square. So, a square is the area, and because of adhesion, okay, this is the amount of energy that remains in the interface. So, it is minus of W A because adhesion is there is adhesion there. So, that is it has to be negative. So, it is minus W A pi a square. So, the total energy that will be equal to U T, okay, and this is equal to 3 pi mu delta cube A to the power 4 by 4 h cube, and this is minus F delta minus W A pi a square. So, this is what it is. So, we have got elastic energy, mechanical energy, potential energy, and the surface energy. So, we add up all that, and now let us say minimize it with respect to A, okay. So, amount of energy that needs to be applied with respect to A, and we do all that let us say over here. So, we have already done it similar thing. So, I am going a little fast here. So, if we minimize it with respect to A, so you put del U2 by del A is equal to 0 here, and that leads to this derivation. So, it is 4 here, and this is 3 pi mu delta square A to the power cube by 4 h cube 2 minus 2 pi A into W A. So, finally, we have this, and this leads to this expression for delta by this quantity 2 W H cube by 3 mu A square. So, this is the critical amount of delta, the pull of distance that needs to be there in order for the top plate to separate from this elastic film, and so now you substitute this delta over here in this expression of f, and that leads to this expression pi f is equal to pi a cube into delta over here, and that leads to this kind of relation. So finally we get this kind of relation. So after simplifying, and so this sigma c, that is the critical pull of load per unit area, so Q stress, okay, F by pi square, that comes out to be like this. So for incompressible or compressible, both the cases, this after those simplifications and all, the relation comes out to be like this. And of course the mu for an incompressible material, it is elastic modulus, Young's modulus by 3, but for a compressible material, mu is equal to E by 2 into 1 plus sigma, remember that. So mu is equal to 2 into 1 plus sigma, this is for an compressible material, okay. So it will hold. So this is the way that for both for compressible and incompressible, and the case in which this film remains bonded, okay, this film remains bonded over here, and in the bottom plate, and in the top plate there is slipless contact, okay. We can actually derive these equations, and we can also derive the expression for the pull of load required. So now let us say instead of slipless, if you have the perfect slippage, okay, then the boundary condition changes. We know that for perfect slippage, okay, for perfect slippage, what will be the boundary condition? So that is boundary condition is that the shear stress there is equal to 0. So that means that the Zx, okay, Zx is equal to 0 at Z is equal to H, like that. So you apply this boundary condition. We have done similar problems in the context of this rectangular geometry, and we can do the similar approach over here, too, and we can obtain the required expressions. So I am leaving that part to you to derive on your own. So we will take a small problem over here. For example, here a thin elastic disc of thickness 1 millimeter is sandwiched between two rigid parallel discs of radius 15 millimeter. Okay. So thickness is 1 millimeter and the radius of this disc is 15 millimeter, such that it remains bonded to the bottom substrate while no slip boundary condition remains valid at the interface with the disc at the top. The Poisson ratio of the film is 0.45. Obtain the characteristic length scale and defines the pressure distribution of such a film, that is L is what I am interested in finding out. Okay. So L is equal to K square by 12 mu. Now if you substitute the K is equal to this expression that we have derived obtained long time back. So this bulk modulus, okay. So here in essence what we have a ratio of K by mu, okay. So therefore what we have here is H square and then a function of this Poisson ratio. So that is the idea here. This particular length scale L, okay, that defines this particular aspect, that the ratio between this now in a sense that defines that about this function, okay, of this Poisson ratio, okay, that's it, and that L comes out to be for this case, for example, very close to H, about 0.9 H, but for other cases, for example, that if sigma goes to very close to 0.5, okay, this quantity L will be much larger than H, or is like that. So we get some idea of what is the kind of like characteristic length scale, okay, this L that defines over here. So that's all about this my what we want to cover in this problem of this sandwiched plate in a circular geometry, circular disc. And now I will go to the next topic, and which is again about a sandwiched elastic film or sandwiched adhesive film, and that is about peel test. So you all have used these Scotch tapes or the tapes of different types. In all these cases there is a thin layer of glue that remains bonded to a plastic sheet, okay, which actually, or a let us say fabric sheet, or let us say paper material, okay. This paper material or plastic sheet, okay, which is the non-adhesive part, that is called the backing layer, and then on that backing layer we have this thin layer of glue, okay, that remains bonded. And then what you do is that we try to know that what is the kind of adhesion, okay, given by this particular adhesive glue on any surface. So let us say we paste it like this on the substrate, and then a substrate adherent, okay, and then we try to lift it. So, this is a very simple experiment for finding out the adhesion strength of an adhesive, and when we lift it we can do perpendicular like this, the picture that I have done shown here, or let us say we can do some angle like this, or we can do some angle like this. In fact, we can also have an experiment in which we directly peel maybe at 180-degree peel angle. So, means the adhesive remains bonded to the substrate over here, and I peel it at almost parallel to the substrate, so that this angle, okay, is theta is very close to 180-degree like that. So, here this angle is 90-degree peeling, this is called 90-degree, and over here this theta should be I should show it like this, theta should be like that. So, now if I have similarly, if this angle is theta like that, so theta is this angle. So, so we can peel it in a different way, and we can obtain the peel force that is required here. So, this is peel force is given as P, and then we want to know that for a given peel force what is the kind of energy, okay, adhesion energy that it corresponds to. So, naturally if the adhesion is very strong, so the peel force will also be large, okay. But how will that peel force depend upon this particular angle of peeling, that matters. So, that is an important thing. And so, this experiment is done normally in a constant rate. So, for example, like that this peeling experiment can be done at a constant rate, or let us say and the rate can be varied. So, how this happens is that we want to see that suppose I peel this particular tape of this particular substrate at a slow rate, then what is the kind of peeling force that I will get, and if I do it at a very higher rate, then what is the kind of peel force that I get. So, it varies. So, that is another thing. So, at rate dependent, so we find out that the adhesion rate adhesion strength depends upon the rate dependent, okay, rate dependent. So, it is not exactly a rate independent quantity for many or most the steps. So, adhesion energy, okay, we find it rate dependent. So, what I mean by this is that when we do this experiment peel test, we have to define this rate, okay, at what rate we did peel this particular tape, and also we have to define what is the angle that we peeled, okay. So, so that we have the complete idea about how things are happening in this case. So, here is a movie, I will just play it for you today, and then I will continue in the next lecture more about this material. So, here is basically an adhesive which is bonded to a substrate, and then from the left, okay, so this adhesive tape is not visible here, but it is being peeled off, and so therefore, there is a separation that happens, and then so here we see that this particular separation is actually, this adhesive remains actually bonded to most of the part, almost all part over here, and now this is getting separated from this part, and when it gets separated, it is not that the separation happens along a continuous line like that, but it happens within a zone, okay, by formation of this kind of cavities and like that. So, this is there. So, these are the kind of things that happen when we try to peel it, and so we may be interested in a very superficially that what is the load that is being applied. So, we will know about the adhesion energy, or let us say if you are more interested, we can go a little deeper and we can find out that what gives rise to this kind of effect, or let us say we want to go even deeper, we want to know that what is the kind of surface, does it allow the slippage or does not allow slippage, and so on. So, this simple experiment, okay, has got this different level of complexity, and as we are interested we can actually look into it. So, let me just play this video, and then I will leave it for you today, and I will come back to this particular problem in the next lecture. So, you will see that there is a kind of a wavelength, a wavy crack front that propagates, and that goes from the left to right, and that is the way that it happens, okay, in this case when you peel this adhesive from a surface. This is a common Scotch tape, okay, that we use. So, I will stop here today, and I will continue with this discussion in the next lecture. Thank you.